In today's lesson, we'll take a look at our first nuclear reaction. It's called fusion. It's when you take two separate atoms, or two separate nuclei, and you cram them together and make one. In our next lesson, we'll take a look at the opposite process, fission, where you take one atom and you split it apart into two. But let's start with fusion. What is fusion? First of all, we have nuclear fusion, and that's the combining of isotopes. So notice over here we have 2H. This is our isotope notation. They've left off the 1, which is implied, which would tell us the number of protons. So remember, this top number always tells us the mass number, that is, there are 1, 2 things in our nucleus, and the bottom number always tells me the number of protons, which here are in red, and we have just 1 proton in this atom. So there we have 1 isotope of hydrogen with a mass number of 2. And then here we have another isotope of hydrogen. This one has a mass number of 3. The only difference is it has 1 more gray sphere there. It has 1 more neutron. Okay, and those collide in nuclear fusion. So in nuclear fusion, we take those two and we collide them together. Now you have to do this at extremely high temperatures and pressures. Temperatures and pressures that are hard to reach most places in nature except the sun. And here in the sun, we have fusion. The main thing going on in the sun is the merging of hydrogen and helium. Remember that we talked previously about how the sun was made of mostly hydrogen and some helium. Well, this is why, because in the sun, hydrogen is combined to make helium. So this fusion process combines hydrogen 2 and hydrogen 3, and they form one nucleus, helium 4. So now that has 4 things in the nucleus. But if you're paying close attention, you might notice that actually doesn't quite balance. There seems to be a neutron that's gone missing. Notice before we had 1, 2, 3 neutrons. And now we just have 1, 2. What happened to that neutron? Well, first, let's try to write this in the form of a nuclear equation. How do we do that? Well, we start by saying we have 2, 1, H. That's just our hydrogen 2. And we're going to combine that with our other hydrogen, which is 3, 1, H. So notice what these symbols are saying. I have 2 separate things and I'm adding them together. That's what the plus sign means. And now to show that I'm going to get something new, I'm going to use an arrow. And that arrow tells me, okay, I combine these 2 things and now something changes. So we could think about this side as being like before some change, and the side we're about to draw as being after. What do we get after? We get 4 He2. That's helium 4. Okay, so that's our after. Nice. We know what we have before and we know what we have after. We've fused 2 things together. We've combined isotopes. Now let's return back to thinking about that missing neutron. This neutron has to be somewhere, right? Remember we said we have 1 extra neutron before. And we can actually see that if we carefully add up the numbers on the before and after. This is a 2 and that's a 3. So if I add those up, I get 5. 5 total things in the nucleus. And afterwards, right now, I just have 4. That's what we call an unbalanced nuclear equation. It doesn't have the same number of things on the left and right hand side. We've changed the number of neutrons specifically. So what we know is that neutron actually still exists. It just comes out of this reaction separately. So it shoots out. It's a gray sphere. And we can actually represent that with 1, 0, N. It's not an element because it doesn't have a proton. And remember, you need a proton to have an element. The number of protons is what defines an element. And so here on the after, we're going to also get out a neutron. And now you can see that we have 5 total things in the nucleus before and 5 total things in the nucleus after. So that's a nuclear equation. Let's take a closer look. Okay, so here's nuclear fusion and our reaction shown, written out a little more nicely. What we need to make sure we have is that our nucleons have been conserved. What is that? Nucleon, that's a weird word. That just means our protons or our neutrons. So it just includes both of those and they can't change, okay? And so when we look at the before and the after, the total atomic number and the total mass number have to stay the same. That's what we mean for nucleons to be conserved. And so notice there, all in the yellow, we have mass number. And on the left-hand side, we have 2 and 3, gives us 5. And on the right-hand side, we have 4 and 1, also gives us 5. So our mass number has stayed the same. Let's check out our atomic number. That bottom one, which tells us number of protons, we had 2 protons before, and we have 2 protons after. So we always have to compare the protons and neutrons we started with and the protons and neutrons we ended with. Now, why is this process important? We've talked about what fusion is. The reason it's important is that it is the energy source of the sun. And the energy released is calculated by this E=mc² equation, which tells us that a ton of energy comes out from these nuclear reactions. And that's actually what you see added over here in these weird units called mega electron volts. We're not going to go into those in detail, but we will talk about how much energy comes out. The way we calculate that is with E=mc². Remember that this c² thing is the speed of light squared. The speed of light is 300 million meters per second. So if I multiply that by itself, that's what squaring does, then I'm going to get something really, really big, 300 million times 300 million. And then I multiply it by mass that's lost during a nuclear reaction. And that's an important point. As these nuclei fuse together, some of the mass is actually lost. And if I plug that mass lost into the M, that'll tell me my energy released. Now, we're not actually going to do this calculation, but what I do want you to understand is that because this equation multiplies the mass by the speed of light squared, you get a huge amount of energy out. How much energy? Well, nuclear reactions release over 1 million times as much energy as a typical gasoline reaction. So if I just burn a gram of gasoline, or I lose a gram of mass in the sun, the amount of energy released by the nuclear reaction will be 1 million times higher than that from the gasoline. Okay, so that's fusion, where we put two things together.
Hey.